As we take a look here at section 7.4, the goal is going to be to understand how we can actually begin to do some calculus with the polar coordinates and polar curves that we talked about in the last section. Specifically here, we're going to focus on the ideas of finding tangent lines to polar curves and arc lengths of polar curves. And in the next section, we'll take a look at dealing with areas enclosed by polar curves. Well, again, if I want to go ahead and start to do some things like tangent lines and arc lengths, one of the most important things that I'll need is to be able to calculate the derivative of a polar curve. But not just the derivative with respect to r's and thetas, but specifically the derivative with respect to x's and y's, because if I want the slope of a tangent line, that's going to be given in terms of x's and y's. Now, fortunately, this is very, very straightforward and easy to do. Notice that if I consider that I have a polar curve that's given by, say, some equation like this, r equals some formula with some thetas in it, then if I want to find an equation of a tangent line to some point on the curve, well, then what I need to do, or I'll say here, to do this, we need to calculate dy dx, right? I need that dy dx in order to be able to understand the slope of a tangent line. But I can think carefully about how I might be able to find this dy dx. Well, let's suppose I do this. I'll say, if we view theta as a parameter, and observe the following identities, I can see something very powerful begin to shape up. We established in the last section that x would always be equal to r times the cosine of theta, and that y would always be equal to r times the sine of theta. Well, if I go ahead here and I update these just a little bit more, I'll notice that in place of r, if r is equal to f of theta, I can just write this as f of theta times cosine theta, and y is going to be equal to f of theta times sine theta. What we've really been given here, then, is a way to describe the relationship of the polar curve with x's and y's, but we've been able to do it entirely in terms of theta. Notice no more r exists in these equations. So again, I can see here that these are now exactly similar to parametric equations like what we talked about in 7.2. And if I knew in 7.2 how to find dy dx for parametric equations, I could kind of reuse that same idea here. So I'll state that we can then use the ideas from 7.2 to find dy dx. And in the theorem below, you'll see how exactly we do this. In order to find the slope of a tangent line to a polar curve at some given angle of theta, what we would have to do is to first do this green conversion, change everything into these parametric equations, and then recall that if I wanted to find the derivative for my parametric equations, I often had to do this dy over dt, but in this case we don't have a t, we have a theta, and then we divided that by dx d theta. So, of course, if I wanted to write this out in more detail, I'd see that, well, taking the derivative of y with respect to theta is actually going to require a product rule here, because notice I have an f of theta times a sine of theta. So, if I was to write out the details of what this product rule looks like, I would have something kind of like this. So let's see, I'd have f prime of theta plus this, or times the sine, plus the f of theta times the cosine. And in the denominator, I'd have to do this derivative in a very similar way for the x. So I'd have f prime cosine of theta, and then an f and a negative sine theta, which is why I left a negative out here. So this is what I would need to go ahead and compute. Of course, all of this is provided that this denominator doesn't turn into 0, as we saw in the last section. So this is a really powerful idea for us to be able to wrap our minds around. If we can understand how to do this green portion up here, how to take a given polar function and transform it into something parametric, then we get to import all the ideas that we already learned from 7.2, and this process should be really, really easy. In the next video, we'll take a look at example 1 and see how easy this is to actually apply to a specific example.